Yeah, I'm holding.
Just it has a 20 seconds delay, so you continue, then I'll confirm with you.
Yeah, this conversation you should be able to hear. It's on.
Yeah, it's working. Go ahead.
Okay, so all right. Sorry for the disruption. I'm starting again. Uh, Good afternoon. My name is Ravinder. I welcome you all to this National Science Day talk organized by Public Outreach Cell of IIA. National Science Day is celebrated every year on this day to commemorate the discovery of light scattering by renowned Indian scientist C.V. Raman in 1928. As you know, this groundbreaking discovery also won him the Physics Nobel Prize in 1930. Raman was the first Asian to receive this honor in science and still remain the only scientist to have won the Nobel Prize from the Indian soil. His fundamental contribution to understanding the nature of light matter interaction has helped solve many outstanding problems in physics and chemistry. The National Science Day has been observed all over the country since 1987 in connection with this discovery. Our universe is full of mysteries. For many of us, the National Science Day is an opportunity to share the excitement and joy of science with people. One of the unsolved mysteries in astrophysics is the problem of dark matter and dark energy. The dark matter is an invisible matter that is everywhere, but somehow does not seem to interact with the normal matter that we are familiar with, except gravitationally. Dark energy is a mysterious force that continues to drive the expansion of the universe. To shed some light on the mysteries of dark matter and dark energy, we have invited Professor Subuni Das for today's Science Day talk. Uh, Subinoy Das is an associate professor in Indian Institute of Astrophysics, Bangalore, working in the frontier of dark matter and dark energy. He completed his master's from IIT Kanpur and obtained his PhD in 2008 from New York University, US. Later, he spent 5 years in Canada and Germany for his postdoctoral research in astroparticle physics and cosmology. He joined IIA as a faculty in 2011. His research interests spans many interesting topics like beginning of universe, formation of galaxies through gravitational pull of dark matter, and accelerated expansion of space by dark energy. Today, Subinoy will talk about the mysteries of the dark matter and dark energy and fate of the universe. Before I invite him to speak, I request the audience to keep their microphone muted during the talk. After the talk, you can use the raise hand feature in the Zoom to ask questions. And if you are watching this program on the YouTube, you can also post your questions in the comment sections. So Subinoy, you can start the talk now.
Okay, thanks, Professor Ravinder, for the introduction. I am audible and visible, my slide, I think.
Yes, you are audible.
Yeah. Okay, so this talk, as it is a public talk, I will remain in a level where even if you know only Newton's law, you should be able to understand at least 90% of the talk. And you are welcome to ask questions, and don't hesitate to ask any sort of question what you feel that you want to know at the end, okay? As we are doing it in the online version, so it will be better if we do all the questions at the end. So let me begin with our perception about this universe. And when we look into the universe only through naked eyes, it can be misleading. You can see that 15 centimeters away from human hair, it looks like this in the left window. And whereas 2.5 million light year away, one of the galaxy, Andromeda, looks like a dot. So if you just see through your naked eyes, you might be misled that what is actually there in the reality. But still, we can do a lot. Our eye is very powerful. And if you are privileged to go to southern hemisphere on a clear sky in the night, you can see in your naked eye the galaxy, the beautiful galaxy with billions of stars. You can see, of course, you will not be able to see the billions of stars, but you can see the galaxy. So this is a quiz question. What is this galaxy, the bigger oval? You can write down in the chat box. And in the left side, there are two small satellite galaxies. So I'll give you the answer. This galaxy is our galaxy only, Milky Way. I know some of you have given the right answer. It's a privilege to be able to see the Milky Way galaxy, our own home. And left side is the top is the two satellite galaxy of our. There are, like we have our satellites, moon, like that. Our galaxy also has small satellite galaxies. So, but the existence of billions of galaxies came through technology, and that's why we need to look out. And for that, we have ground-based telescope. In fact, our institute, Indian Institute of Astrophysics, is leading the astronomy program of India. And in near future, TMT telescope, one of the biggest telescope from ground-based telescope, is coming up. And now there are also space telescopes, and through that we can see amazing picture, capture the amazing picture of galaxies. And these are some of the pictures. These are not artist drawing. These are real pictures from some of the telescopes. And you can see a typical galaxy. It's really so beautiful looking when you look into this picture. Is like amazingly. They're existing around us. They are nearby galaxies. And typical galaxies are like 60,000 light years across. That means light will take 60,000 years to travel from one end to the other end. It's pretty big. And around 10 billions of stars on an average. And they're not static, they're rotating. And it takes around 200 million years to complete one rotation. And the rotation speed, for example, in our Earth, where we are a little bit far away of the center of Milky Way, it's around 300 kilometers per second, pretty fast. So it feels like static in the night sky, but nothing is static in the universe. So now, basic fact about our universe. So there are billions of such galaxies in our universe. Like what you see, 1 galaxy, 2, 3 galaxies, like billions of such galaxies. And each galaxy has billions of stars. So you are really not even a speck of a speck of a speck in this vast universe. Okay, yet it is fascinating that we can experience and we can explore the universe. And even not only that through visible eyes or what we can see. Today's talk, you will see that we have the power to explore even the unknown of the universe, which is called dark matter and dark energy. So basic facts about the universe. Universe is pretty old. And how do we know that it is 13.8 billion years old? There are old things in the universe. For example, Earth is 4.5 billion years old. Sun is 5 billion years old. Oldest stars are 13 billion years old. And there is something called fossil radiation, microwave background radiation, which have also got Nobel Prize, which was almost like the echoes of Big Bang. And that tells us that the universe is 13.8 billion years old. So pretty old compared to our human existence of 100 years. And the universe is also very big. So this is the length of the universe, our visible universe. I'll not read out how many miles it is, because that's not the unit we use. We use the light years, and 1 light years is, you can see in the yellow, I have given the number 6, then 12 zeros miles are 1 light year. So like that, 30 billion light years is our universe. So it's very, very big. Just to give you an idea, so light takes 30 billion years to travel from one side to the other side of the universe, whereas light takes to around 8 minutes to travel from Earth to Sun. You can keep yourself unmuted. Some of your noise is coming. And so 8 minutes is pretty big, because from here to sun, I once calculated that if you have the super fast jet plane, and if you want to reach to sun, it will take 15 to 20,000 years in the super fast jet plane. Light travels that in 8 minutes, so it's pretty fast. And that same light takes millions of years to cross one galaxy, and billions of years to go from one side of the universe to other side of the universe. So it's pretty big. So this is the story. Like, we all have our stories of life. So cosmology is nothing but studying the story of the universe. And from its birth to its fate, we don't know what will happen, but we are somewhere in the middle, or we are somewhere towards the end. We'll come towards the end of the talk today. But whatever we have known through our technology and our spirit of inquiry is fascinating. If you tell these things like 100 years back to somebody that these are the facts we know about our universe, nobody would believe it. Yeah. So today I will share with you that where we are heading towards about the story of this universe and what has happened and what are the biggest question about this universe, where everybody asks, whether you are a scientist or not. I'm sure everybody asks some of the fundamental questions about this existence, about this universe, especially when looking to the night sky. One such question is, where do we come from? Where are these billions of stars? How they are generated, or how are they are there forever? Then the next question is what we are made up of, and what is our destiny? So these are the questions which we look into today, and scientists have been trying to answer these questions. Maybe philosophers also has tried to answer these questions. But today we'll see that the scientist has, the more we wanted to find out the answer to these questions, the mystery got deepened. And today I'll take you into two such mysteries of the universe called dark matter and dark energy. So the first thing all started just to find out that this vast one galaxy, for example, our Milky Way galaxy, 10 billions of stars, what is holding them together? The one answer, everybody finds that there is the attraction, the gravitational attraction, the same Newton's law. And we thought so, but always as a scientist, we went to check that whether the gravitational attraction is enough to hold the 10 billions of stars, because every star is rotating with a huge speed. And you know that when you are taking a turn in a highway, you are driving or a bike or a car, if your speed is high and you are taking a turn, you feel a centrifugal force. And that force will be balanced, has to be balanced by some sort of force, otherwise you will be flying off. And one amazing scientist, Vera Rubin, she wanted to check that whether this is balanced, the force of centrifugal force, because the stars are moving very fast, whether it is balanced by the amount of gravity we have, because we know how much matter we have, how much mass we have, because we know the number of stars, and we wanted to balance. And what she found is something amazing, a little bit shocking. And let's watch a video, because as it's a public talk. So this video credit goes to Professor Brian Green. He was my PhD advisor, some part. So let's play the video, and you will know from where all this started.
This is? Anybody know who this is? Zwicky, yeah, Fritz Zwicky, who was a Swiss-American astronomer, kind of a wonderful character, but he began to study the motion of galaxies in the Coma cluster. This is a few hundred light years away. And again, he found that the motion of the galaxies was such that it couldn't be solely due to the ingredients that he could see by virtue of their light. He concluded that there had to be additional dark stuff that was out there that would be responsible for the gravity that was pushing and pulling these galaxies around. But it was really the work of this person right here, Vera Rubin, who really cinched the case in the minds of many physicists, many astronomers, for the existence of dark stuff that's out there. Because what she did was she studied the motion of stars in swirling galaxies and found that the galaxies are swirling too quickly. The stars should be sort of ejected outward. One way of thinking about this, we can do a little quick demonstration of this. If you have, for instance, a very simple pedestrian situation where you have a wheel, right? And you have water on the wheel. Now, we all know, we don't have to do this, but it's sort of fun to see it. If you take this wheel and it's spinning slowly enough, very little water will fly off, but of course, you give it a real spin, and the water droplets fly right off. Thank you very much. And the idea was that the galaxies are spinning as fast as I was spinning the wheel, so that the stars should be flying off, as the water did. But Vera Rubin found that the stars are not flying off. And therefore, there had to be something else that was pulling them in, something else that's dark, because we don't see it, giving rise to the gravitational pull that was holding the galaxies together. And of course, it wasn't just pictures. There was mathematical analysis behind this. When you do the mathematics, which you won't.
So the expectation is you should be able to see the velocity should fall down. But what Vera Rubin found, that the velocity is actually much higher, and without a hidden matter, you cannot make them bound in the galaxy, because they will fly off. Velocity is very high, and the centrifugal force will be very high. So that tells that there is hidden matter even within our galaxies, which we can't see them. And once you measure exactly mathematically that how much they need to be, it seems like they're much bigger than all the galaxy, all the visible star mass. It is 27% of the universe, whereas 5% are the visible stars and all the things in the universe. So this was a remarkable discovery, that we have many more hidden things in the universe, and the most 27% of the mass of the universe is actually hidden, and you cannot see them. They do not interact with us like the other particles do, but still they exist. And today we'll soon know that not only they exist, they are also the cause of our existence. Without dark matter, we would not be here. So now you might say that maybe this one experiment, there is some problem in measurement, or maybe we don't understand the gravitational laws in our galaxy. That's why we are seeing this curve is not matching. But that's not the story. There are many other experiments which has shown the existence of dark matter. So one such thing is called the gravitational lenses. So this is a cluster of galaxy where many billions of stars are there, and behind is the dark matter. And what you are seeing in the picture is each picture is one galaxy, each small bright object. And you see some of those pictures are distorted. They are like the lensed object. And you can see below in the right that if there were there are dark matter clump, they can bend light. That was the discovery of Einstein. Even our sun bends light. When there is huge, massive object, it actually bends space and time. And that's why anything which travels through the space has to bend. And that's why how much mass is there, it depends on how much bending will happen. And we can exactly map by our computer programming, looking at the bending of the galaxy, that how much mass is hidden behind. But before that, let's watch a short movie again about the bending of space-time, because that will be needed for our dark energy discovery. So this was all started.
And the force keeping the moon
from Newton
orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the Earth in a single theory he called gravity. After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time.
And the space-time can be bent, as I said, when you put object. And the gravity is nothing but the bending of space-time. And when sun evaporates, it will not happen, so don't worry, but it may happen, may collide with another star. Then there will be ripples in the space of empty space, which is called gravitational wave. 8 minutes it will take to hit our Earth, and then only Earth will fly off. So these waves of emptiness proves Einstein was really a genius, and it also got Nobel Prize, that these waves of nothingness, empty space, is really there, especially when two black hole merges. So space is not nothing. So if you move everything in this room where you are sitting, what you feel is nothing is actually not nothing in modern physics. It can bend, it can twist, and in fact, the bending of the space and time makes everything rotate. The moon is rotating, as you see, around the Earth because the space is bent. And the sun is rotating around the galaxy because the space is bent. And that's why the light curve, the lenses we saw is exactly because of the bending of space-time because of dark matter. And this is the computer-generated simulation looking at each and every images of the galaxy which got bent because of the presence of dark matter behind. We can map back and how much dark matter is there. And you can see every spike here is actually a galaxy, and the mountain-like structure below is the dark matter. So the mountain is the dark matter and the spikes on it are the galaxies. So you can clearly see it's the dark matter which is holding the visible universe. This is fascinating. And it matches exactly with our description of evolution of the cosmology. So now we are going to see something even more amazing, that how long this dark matter has to be. The answer is almost from the beginning. You cannot say that dark matter I can produce, say, after 2-3 billion years. No, you need dark matter. Actually, I did recently work with a group in Stanford. We came up with a theory that maximum 7 days you can wait, but within 7 days, you have to produce dark matter. If you produce dark matter after 14 days in the universe, you'll not be able to match the galaxies what we see today. And how? The answer is, we can actually, through supercomputing simulation, we can generate the universe, what we see in our computer, and we can match it, whether it matches with our galaxies and galaxy clusters. And this is called very powerful supercomputing n-body simulation, through which we are mocking the 14 billion years of evolution in maybe 2 months of supercomputer run. Okay, so let's see what it says. So this tiny picture, what you see is just after Big Bang. Universe was very dense and all gas. The Big Bang gave rise to the space and time. Before that, there was no space and time. And then in space-time came the matter in a very hot plasma state. And then it's the dark matter which starts acting on this matter, dense matter, and start clumping. So there are two things going on here. One hand, the dark matter wants to create galaxy because it wants to pull everything together, produce, create stars, galaxies, everything. And on the other hand, we know that the space is expanding, as we know. We'll see it in much detail, that our universe is an expanding universe. So there is a competition between gravity and the expansion of the space. And luckily, the gravity won in the first 10 billion years. And that's why galaxy could be formed. But for the last 4 billion years, or 14 billion of years, first 10 billion years, gravity could win over the expansion of the space. That's why we can create galaxy. Not we, the universe can create galaxy. But last 4 billion years, the story is different. Now gravity actually loses over the expansion of the universe, and that's the dark energy. So we'll see later that if dark energy would kick in a little bit before, there will be no galaxy and there will be no life and there will be nobody to watch this talk today. So let us first see how galaxy is formed by the pool of dark matter. So the blue space is void. The void is becoming more void. And our universe is like a filament. The whole galaxy clusters is like filament. And it matches exactly with our observed universe. So this snapshot, what I show you in 5 seconds, is actually 14 billions of years of, actually 10 billions of years of universe's evolution. Universe waited a lot for the galaxy to be created. And then finally the life came billions of years back. So now we'll move to something different. The story is still now 5% we know about these visible atoms, galaxies, clouds, hydrogen cloud, helium cloud, everything visible, which is seen or unseen yet, but can be seen through powerful telescope. But then comes the dark matter, which cannot be seen through naked eyes. But how do you know that they exist? By their indirect effect, as we see, the velocity. Because once the dark matter is there, its pull will make the star move faster. And that's what we have seen, Vela-Rubin's discovery. So it's gravity which actually makes everything under its influence. So though the dark matter is not visible, through gravity we can feel their presence. That's what. So now we are going to move to the even greater mystery, which is 68% of the universe remaining, is called dark energy. So what is that? Actually, by the way, this got Nobel Prize, the discovery of dark energy, the existence of dark energy. But what is dark energy, we still don't know. In the same way, what is dark matter, we still don't know. Then for the last 20 years, starting from Switzerland CERN, where the God particle was discovered in Hadron Collider, starting, and also satellite experiments, underground experiment, we are hunting for dark matter, but not yet successful. Who knows what it is? We have some speculation, but we don't know what it is. Whereas dark energy is even more mysterious. We have actually no idea what it is, but we know it exists. So how does it show us that it exists? That is our next part. So this is a very historical picture, because right side is Edwin Hubble, who discovered the universe is expanding. And it is actually called Hubble's expansion. Whereas Albert Einstein, who believed that universe cannot expand, universe is eternally static universe, forever it is there. But when this is a rare picture, and later Einstein had to believe that universe is expanding. That's the science is. You might like something, might dislike something, but what is, it is. And Einstein called that it was his greatest blunder. And what was the blunder? Because Einstein knew that from his theory of general relativity, once the space and time got created from Big Bang, you cannot keep it static, it will expand. So he added something called cosmological constant mathematically, which is kind of an attractive gravity, which will stop that expansion of the space-time and make the space static. But then he withdraw that term because he knows that space is not static. So now we'll see that what is happening to that space. If it is not static, what is happening with the space? The belief from the Einstein's general relativity is that, not only belief, we all expected that the expansion rate is actually slowing down. So it is like that. If I throw this cell phone, or I'll not throw it because it's costly, but if I throw it, it will go up, but it will slow down, and then it will turn back. And that's what we were expecting. Either space will slow down forever or it will turn back. And there were a team of astronomers, two teams actually. They were trying to measure the expansion rate, but how much it is slowing down. Now you cannot measure the rate of expansion of space in this classroom. You cannot experience the expansion of space in our solar system. Only way you can experience the expansion or measure when you go in between galaxies, because they are not yet gravitationally bound that much. Here, gravity has already win over it, so you will not be able to, space will not be able to pull them apart. And you cannot see space. That's why you cannot see the expansion of the space. But you can only see the expansion of space when two objects in the space is moving away from each other. And in fact, everything is moving away from each other. And that's why you have to look for further objects like supernova. And I'm coming to that. And these are the two teams who are looking for, it is a painstaking observation. Hubble was trying to measure it, but he could not. The technology was not enough. But only in 1998, a little bit before, people got the technology, and in the US, two teams were parallelly trying to measure that, how much space is slowing down and what will happen to the universe. And what they found is amazing. It's shocking, actually. They found the space was slowing down for 10 billion years. That's why galaxy could form. But for the last 4 billion years, almost when the Earth is born, Earth is 5 billion years. From there, the universe has started accelerating again. It's very funny and very shocking. It is almost like, because we know that gravity was slowing down, because the Big Bang was, after the Big Bang, things are going away, but because of the pull of gravity, things are slowing down. It is almost like the phone is going up, I'm slowing down, but suddenly one day you throw your phone and suddenly you see, like, without any fuel, it's launched like a rocket and vanishes in the empty sky. Exactly, that is what the astronomers found. And then the question comes, what made it happen? What made the space suddenly accelerate? And that is called dark energy, because there is no matter we know, not even photon, electromagnetic radiation, not even anything can make the space repel. This was completely unexpected. So only a rare form of energy called cosmological constant or vacuum energy, or the energy of emptiness, can do that. And that is also very mysterious. So how do we measure the space is expanding? This is called supernova, type 1A supernova. Some of you might know it. It's very interesting. The background, you see a galaxy, and in the left bottom, you see a bright star, but this star, one star cannot be so bright like almost like the galaxy in the background. When the stars burst into supernova explosion, thermonuclear explosion, then only for 3 weeks in the sky, its brightness reach maxima and then it falls off. So only for 3-4 weeks you will see it, and then you will see that they are gone. But once you see it, you will see it with the same power. That means it doesn't matter whether one type 1A supernova is bursting in our galaxy end or other galaxy or nearby galaxies. All the time their brightness is same, say 100 watt. So not 80 watt, not 70 watt, not 90 watt. Whenever they burst with 100 watt. So that is a gift to us, because if we know that they are all same watt, same power, then if they look dimmer or faint, that means they are farther. And if they look brighter, that means they're nearer. And through that, you can measure the distance. And that's what the astronomer did by looking at finding the supernova. It is not so easy. It's very, very hard. And then they mapped the distance and they saw that what is the velocity they are going away from each other. And they found that they're actually speeding up in each direction. So it is not just one supernova going each direction, they are speeding up. That means space is speeding up. So this is almost very mysterious. It almost feels like this video.
Slows the ascent of an apple tossed upward. The gravitational pull of each galaxy on every other must be slowing.
But they found it speeding up.
Faster and faster. That's like tossing an apple upward and it goes up faster and faster.
So this is mysterious. And this is dark energy. And once you measure that how much dark energy is needed to match the expansion rate, speeding up rate the astronomers found, they found it is the 75% of the universe, 70% of the universe. So our universe, now we know. If you ask astronomers or physicists 60, 70 years back, we thought we know almost 100%. There are a few unknown over there. But now, the more we have known, we realize that 95% is unknown. So mystery got deepened. So this is the state of the universe right now. We know that the above is our iceberg. It's like the Titanic, going, and the tip of the iceberg is our visible universe. So many particles, quarks, neutrinos, all these things. But the underlying is 95% is the invisible, and they shape our universe. So now I'm going to show you something. I'm now moving towards the fate of the universe, which is related to this dark energy. And it is not just speculative that the space is, we can measure it. And next generation, even in IIA also has this TMT telescope coming up, then dark energy telescope, so dark energy survey, where we can actually measure the evolution of last 4 billion years, that how much speeding up and when exactly speed up happened, and whether the speeding up rate, the speed of speeding up is changing, because that will determine the fate of the universe. If the speed of speeding up, in scientific term, it is called the double derivative or the triple derivative, speed of speeding up. It is positive. If it is positive, then we will have something called catastrophic expansion at the end, few billion years from now. The expansion of the space will be so fast and rapid that it will tear apart even the molecules and the atoms. So there will be nothing. Everything, even the quarks will go away. So, but we believe that that is not the case. We believe that the expansion rate is positive and speed of speeding up is positive, but it is not a catastrophe. But what it is that I'm coming now. What is the fate of the universe? So once we measure the amount of dark energy needed, we got a number, because we know how much energy you will need so that it can infuse the space so that it can accelerate the supernova. Space is going. It is amazing. From Einstein's general relativity, you can actually map that how much matter or energy is there, and that will determine how much speeding up is happening. This is unbelievable. And once we do that, this is what we found, a number which is so tiny in natural units.
This number is small. Expressed in the relevant units, it is spectacularly. The different shapes yield.
So now I will explain it a little bit. That it is small, but it is enough for speeding up. Now this number has so many zeros, and then the scientist asked the origin of this number. This is very philosophically interesting. As I said, out of these so many zeros, if you have a theory where there are a little bit less zeros, say 2 zeros are not there, 3 zeros are not there, it's like, what is a big deal? I have 120 zeros here, maybe 3 zeros are, anyway, it's a very tiny number. Suppose you go to buy a cup of tea and you have tea prices is 10 rupees and you give to the tea shopkeeper that I have 9 rupees 90 paise or 9 rupees 99 paise. You will not mind. But here it is a big deal, even if you miss 1 paise. What is the big deal? As I said, if you erase 2 zeros here, that means you are increasing the amount of dark energy, which is cosmological constant. That means it will take over the universe, the accelerated a little bit earlier. As I said, for 10 billion years, dark matter was winning over expansion. It is the dark energy when it steps in its foot, and then dark matter loses its game. Now, in this very expanding universe, rapidly expanding universe, you cannot create new galaxies which are already not bound in the gravitational object. Of course, you can create galaxy in the galaxy cluster, but from large distance, the space is winning over it. So now the question is, if this number was a little bit small or a little bit bigger, say you erase 3 zeros, then you can show that we might not be even form our Milky Way galaxy. So this small number, sometimes you cannot just say like, leave it, it's a small number. No, it is related to your existence. And one such answer to this puzzle is there are multiverses. That means there are many universes with many different numbers of dark energy. And we happen to be in a correct one with so many zeros, 1 through 8, so that for 8 to 10 billion years, dark matter can win over dark space expansion, form beautiful galaxy, and intelligent life can form, and we can all celebrate National Science Day. But in other universes, who knows, maybe other forms of life, and this idea is not just a speculation. In string theory, In the beginning of universe, you create, they say there are different dark energy dominated universe comes, and each universe is like one bubble floating in an eternal space of eternal universe. And one such universe is we are, and we happen to hold the intelligent life. Here is very similar to ask this question about that why Earth is so privileged to host intelligent life. These questions were bothering many scientists, and now we know there are many such Earth-like things, and Earth happened to be in the right distance with the right temperature where life can sprung. But here we don't know whether there are many universes. We even don't know what is the boundary of our own universe. So we are yet to conclude. So that's why it is a very controversial explanation. And still, this is the only explanation we have on this small number. So let us see what it says about this.
Yield different physical features, and we find ourselves in one.
Each one is a small, a big, one bubble of universe with different number of.
That the physical features, like the amount of dark energy, are right for our form of life to take hold. And this is the compelling but highly controversial picture of the wider cosmos that cutting-edge observation and theory has now led us to seriously consider. But because of the law.
So now we are coming towards the end. So this is a mystery, that why this number is so small, people are trying hard. So there are, and the beautiful thing is the astronomy, the observation can shed light into it. This theory assumes that the dark energy density is constant, that is, it is called cosmological constant. But within 10-15 years, either through dark energy survey or through TMT, we'll be able to tell that whether this energy density is cosmological constant or something else. If it is something else, because looking at the evolution of the last 4 billion years, you can exactly tell how much energy of dark energy is there and whether they're changing with time. If they changes with time, then this whole idea of multiverse will be dumped into the garbage box. So that's amazing that even the experiments in last 10-15 years will be able to guide us to understand whether there are multiverses or not. And now the fate of the universe. We believe that this is the picture that cosmological constant dark energy is really a constant with a tuned value, which can host life. And if it continues to do that, because it's a constant, it will continue to win over the attraction. And then this is what happened. Few billion, 4 or 5 billions of years later, if there are astronomers looking in the space, they will see what I'm going to show now in the video.
The laws of physics. The light those galaxies emit, even traveling at the fastest speed, the speed of light, will not be able to overcome the ever-widening gulf between us. So astronomers in the far future, looking out into deep space, will see nothing but an endless stretch of static, inky, black
stillness. So they will see that there is no galaxies because everything has been pushed upward. Maybe our Milky Way is the last one holding because the gravity has already won over it. But if, as I say, the speed of expansion is speeding up, then this will tear apart our Milky Way also, but we don't know what it is now. But even that will be fascinating. Say, of course, none of us will be there, but 4 billion years later, if they see our papers, scientific papers, we have discovered billions of galaxies, published paper, they will say like what our ancient people has done because they don't see any galaxies. They see they are the only one. They are correct and we are correct too, but they will not believe us, okay? So we are living in a very privileged time. Sometime universe reveals its secret, deep guarded secret in this privileged time because now we can experience dark energy, we can see the dark matter, and there are a lot of unknown, and that's why for youth, for like future astronomer, there is fascinating time. And India is also, as I say, building up telescopes, and this research really needs intelligent brain and hardworking scientists. So this is how I'm going to end, that 5% visible matter has got so many Nobel Prize, so many particles, so many forces, but maybe we are just going to try in the beginning of probing an unknown world. Who knows, there may be unknown galaxies, unknown stars, who knows? So many fascinating things are ahead. And that's where I end my talk today, and I'm open to questions. So thanks, Ravinder.
Thanks, Subuni. That was very interesting talk. And we have seen many people were asking questions. So I think since it's a question time, the audience can use this feature, raise hand feature, and then I will ask them one by one. So please raise your hand and then we will ask the questions.
You can directly ask or type it down, then Professor.
So, okay, let me just ask. Pratiksha is asking, did universe create itself?
So this is an unknown question, unknown answer. The question is the right question. Stephen Hawking has given a theory that with quantum origin, from nothingness, from wave function, you can produce the universe. So it's not an external thing. From nothingness, the universe can create the space and time. There is some theory, but we don't know whether that is true or false, but there is theory. There is mathematical derivation from quantum mechanics. Yes, next.
Divanshu had asked some question regarding the dark matter. So Divanshu, I think you have not paid attention. Probably your question was answered, but I will just repeat it. So how do we observe dark matter, and how dark energy is different from dark matter?
I think I have answered all these things. Yeah. But I can just tell one or two sentences.
Yeah,
the dark matter is discovered by looking in our galaxy, the speed of the stars, because you need more hidden matter, so that more attraction, so that more speed up is needed to balance that force. Whereas dark energy is the expansion of the empty space, which we found through supernova expansion. Yeah.
So there's a question from Vishal, and the question is, can string theory be considered as theory of everything?
See, once you have theory of everything, then the problem is, if your prediction should be on certain level, because if it can predict everything, then you cannot verify it. Okay, so that's why once string theory come up with a specific prediction which is verifiable through CERN or through some other cosmological experiment, then we'll know that whether it is the right theory or not. Now it is an open-ended question. We cannot conclude that whether it is the theory of everything, but it is one of the promising theory which gives you some clue about the origin of space and time.
Yeah. So Anushka had asked, why does ratio of dark matter and dark energy huge?
Why the ratio of dark matter and dark energy huge compared to our visible matter? Maybe that's what the question. Yeah, that's how it is. So 5% we have got, and 25% is still matter. And we know that if the ratio is something else, then it will be problematic. As I said, that if dark energy will be 75% or 80%, then it will dominate the universe acceleration much before and will not be here. So it is also in same sort of answer that the ratio has to be in this ratio so that you can ask the question. But we don't know that. I know what you are asking, but there is no fundamental origin that why this ratio is like, because we have not determined what they are yet. Yeah, next.
So Divanshu has asked another question. Does black hole contain dark energy and dark matter?
Okay, very nice question. So till now we believe that black hole is not dark matter. But recently, because of the LIGO and other gravitational wave detection, we realized that black hole which are created, they are called primordial black hole, means much older, billions year older black hole, not formed in our galaxy later, but much before, maybe from the radiation dominated universe, much before that, during the CMB time, cosmic microwave, they can contribute to some fraction of dark matter. And the Gravitational Wave Observatory is looking forward to it. And there is a peculiar mass of such black hole. If you find that mass of black hole, then you can tell that they are not the stellar black hole, they are the primordial black hole and they are the dark matter. So if you hear in the news in next 1, 2 years, 3 years, discovery of primordial black hole, definitely it might get a Nobel Prize and it's a eureka. So good question. But normal black hole cannot be dark matter. They are very tiny in number. They cannot produce the amount of dark matter we need in our galaxy. Yeah.
So Samiksha's question is, does virtual particle come under dark matter?
No, the dark matter has to be stable. It cannot be. We know that virtual particles are transient. They appear in collider and they march back into something. But dark matter has to be stable from the first week of the universe, 7 days maximum, till now. So 14 billion years, it has to be stable. So it cannot be dark matter, but it can be some other unknown fundamental particle beyond our known particle of standard model. But it cannot be virtual particle. Next.
So Vishal is asking another question. Can time be made up of fundamental particles just as matter?
Sorry, can you repeat it again?
Can time be made up of fundamental particles just as matter?
Time? No, the time is mysterious. It is different. It is a dimension. It is not a particle. And we still don't know what time is, but because we know that it is a dimension, space-time dimension, but it is different than space because time flows in one direction. Space, you can go minus x direction, plus x direction, both direction. But time, you go only in one. You cannot do time travel back. So we don't know what it is. It's a big open question that what time is, but it is not a particle. Okay. Yeah.
Yeah. So there was another question. Is the antimatter same as dark matter?
No. Every particle has their antiparticle, and dark matter also may have their antiparticle. It is believed, with the model of dark matter we trust, we have not detected it yet, it is their own antiparticle. Means their antiparticle is similar, same as their particle. Okay, but antiparticle, even electron has antiparticle, we call positron. So they are not dark matter. Antiparticle can be produced in the lab, in Switzerland, in collider, and it can be observed, but dark matter has not been observed yet. Yeah.
So Padmashri wants to know, did we detect traces of dark matter with xenon 1T experiment?
Okay, this is a little bit technical question. So recently, for a few months back, xenon 1T experiment has found some signal, and it is not the normal dark matter we all expected, called WIMP. It is not WIMP, weakly interacting massive particle. It may happen that it has detected some other fundamental particle, like axion or other thing, but we cannot say for now sure that it has detected dark matter. But it's a very interesting result, and further results are awaited, and then only we will be able to conclude. Because now we have to be sure about the error bar and the fluctuations. Yeah.
So Morey's question is, if the theory of multiverse is correct, is it scientifically possible to visit another universe?
You cannot visit another universe because it is causally disconnected. That's why I call our universe is causal, because even light cannot come from that universe to our, because in between the space is expanding even faster than light. But what can be luckier or luckiest is sometime one universe can have collision towards the boundary of one universe, say for our universe. And that collision can imprint in the cosmic microwave background. And there was a speculation that maybe some universe boundary has collided with us, but that speculation is not, it was 10, 15 years back, people have started studying that, because they saw a distortion in the microwave sky in all directions. In one side, there was a distortion. They said maybe it is a collision from other universe, but that theory is not so popular anymore. So it's very unlikely that we will see multiverse colliding with us, another universe. But there might be some other way, I don't know. Okay, but we cannot travel there with these physical laws. It is bound by causality.
Now I will take some questions from YouTube. The YouTube viewer Parsharaz Kagli, his question is, can there be anti-dark matter? What is the distribution of dark matter in our galaxy, within our solar system, etc.? Since what time did the dark energy form? Is it forming still?
Okay, the first answer is dark matter is distributed all over. it has some density profile. Towards the center of our galaxy, it's very high, but as you go away, it falls off, But in our solar system also, we have dark matter, and even in this room where I am sitting, you are sitting, if we increase dark matter, we will expect every one teacup. My cup is pretty big, half cup, one particle of dark matter of 100 GeV. So they are floating around, but there is a wind of dark matter going on. And because we are moving through the galaxy very fast, our solar system, whereas dark matter is kind of stable, like a cloud. So it is like an aeroplane moving through the cloud, looking for turbulence, but we don't feel the turbulence because dark matter does not interact with us. But we are moving through the dark matter cloud. Now to answer your second question about dark energy, when did it form? It is formed from the very beginning. As I said, that every universe is given one value of dark energy with the most accepted theory, because there is no other theory of dark energy, only one or two. So it is there from the beginning, but its value is such that it starts to dominate after 10 billion years. Yeah.
So the question from Dola Sena is, how do we observe the exact size of universe? That is
we can measure the farthest observation, because see, if universe is 13.8 billion years old, then the light which was in the beginning after CMB, cosmic microwave background, they are in the baby universe, just 0.3 million years, which is like in the beginning of universe. They're still traveling to us, and their wavelength is in that's why it is called a WMAP experiment. No, they have that's got the Nobel Prize with the antenna. Normal antenna, you can detect them microwave background. By detecting them, and you can say that because you can find their wavelength and everything, and there is a theory how they have originated from hydrogen recombination, you can say how far they are looking at their wavelength. And then you can see that in every direction, it is like a plasma TV of microwave direction with a sphere, and which is 13.8 billion years away. So that is kind of the boundary of the universe. But if we observe something behind that, then we'll know that universe is even bigger. And that is what we are looking for, called gravity wave from the Big Bang, stochastic gravity wave. And that will be the earliest event of the universe. But till now, the earliest epoch is cosmic microwave background. And that distance is almost billion light year away only. So that's how we measure. And also the distant star, which is far away billion, then we can measure their distance. So we can see how far they are. Yeah.
So there was a question from Ruthvik. He wanted to know if solar system has the dark matter.
Yes, of course it has. Even the room you are sitting has dark matter. We are going through the cloud of dark matter. If dark matter is at all there, the way we thought, most probably it is there. It is there.
Yeah, and there was a question from Sarah. Where does the star disappear after supernova explosion? Where does it disappear?
Yeah, for that you need to study the stellar physics course. You know that Chandrasekhar has discovered. So supernova explosion happens when the white dwarf mass become 1.4. It accretes some mass from nearby, and then there is instability, and thermonuclear instability happens, and the supernova explosion happens. And these are very well-defined problems in astrophysics, and how much mass is needed for them to become black hole, how much mass is for them needed to become white dwarf, and what will happen to the supernova remnant. All these things are well studied. Okay, so you can search even in Wikipedia. Today we don't have time to go in detail.
Yeah. So, Crispin, how much time do we have? I think probably it's time to wind up. There are lots of questions, but probably we don't have so much time.
You can give my IIAP email ID, subinoy@iiap.res.in, in case some unanswered questions are there. So you can type, Christopher, because I see.
Yeah. It will keep you busy for a while. Several questions. So maybe, Crispin, can you just give Subinoy's email ID so that people can write to him directly? Yeah. Yes. Maybe meanwhile, I'll take another question from Shashi Shekhar. how does matter affect material properties in terms of their characteristic property? I don't know what it means, but
I think the question is
dark
not
matter.
clear.
So dark matter doesn't really affect the matter that we are familiar with.
Yeah, because it does not interact with us.
Right. So there is a question from Atharv. Is there anything like anti-dark matter which causes gravitational contraction?
No, the mass is positive. Mass is not negative. So that's why even if some antiparticle is there, they will only do attractive gravity. So that's the beauty. Any matter will always have attractive gravity. And that's why you need dark energy to have repulsive gravity. Yes.
Yeah. So maybe one more question. It's about why do we have only four fundamental forces, or why do unified forces split into four?
There may be fifth. We have not discovered it. There is speculation there might be hidden forces in the dark matter. So why there are, but also we know that the three forces, electroweak, strong, and the electromagnetic, they were actually one force in the early time. And then they become diversified and become three different forces. And there has been Nobel Prize for combining electroweak force together, and there is theory. So it's basically one force manifesting, but gravity and the other three is yet to be combined. They are called grand unified or quantum gravity theory. We yet don't know. So not different forces. Maybe the one force is manifesting from the creation to in different forces. Yeah.
So last question now from Akinchan. It's a standard question that is asked almost in every talk on dark matter and dark energy. And he says our universe is expanding, but where does it expand into? Where is it expanding? What does it mean?
Yeah, so there are two answers to this question. First of all, what is not the answer I'll give you? It is not expanding into something else. So it is already infinite and it is expanding into itself. That's why it is infinity. So it is almost like you have infinite ocean and then the water is bulging up because of high tide and never it is a low tide. And still it remains in ocean only. And we are a tiny observer in one part of the ocean. We are seeing that water molecules are going away from each other. So it is like infinity expanding into infinity. There is no outside thing, okay? So you will not be able to visualize this, but that's what it is. That's why many things in modern physics, even the space you cannot visualize. Space is not something emptiness, it is something. So that's why you have to live with it, okay?
Yeah. So I think we do not have more time to take some more questions, but this should be enough for today. And I would like to thank our speaker again, Subuni, for giving this excellent talk. And thank you to all the audience also for joining this public talk on Science Day. I have a small announcement to make. So we had the science quiz competition this morning. And those who have participated in the quiz, they can check out the result about the winners on our outreach web page. So the results are announced. You will be able to find them in IA's outreach page. Probably Crispin would give the link to that page. Isn't it, Crispin? Would you just... Yeah, winners will be informed, and we will also update our outreach page, web page, where the names would be announced. So thank you very much, and have a nice.
Thank you.
Ravinder, there is a question about video contest. Somebody is asking about the results of video contest. That will also be put up on the web page?
Yeah, I think so. Yes, all the results about all the competitions will be on our IA outreach page. And the winners will also be announced by email. So that will happen. So maybe in a couple of days' time.